Imagine for a second that you buy a piece of heavy industrial equipment.
Okay.
You pay a massive premium for it. And then, over the next 10 years, the electricity required just to keep that machine turned on ends up costing you 6 times more than the actual purchase price.
Which is just a staggering thought.
Right, it sounds completely hypothetical.
Yeah.
But that is actually the daily grinding reality of industrial manufacturing. So welcome to the deep dive.
Glad to be here.
Today, we are looking at a highly technical brochure for Hitachi Global Air Power's Solaire S Energy encapsulated rotary screw air compressors. Specifically, we're looking at the 11 to 18 kilowatt or 15 to 25 horsepower models.
Yeah. And I mean, this is the kind of dense, really specification-heavy document that usually just lives its entire life in some maintenance office filing cabinet.
Exactly.
If you were just glancing at it, it's basically nothing but dimensional drawings, electrical requirements, and, performance charts.
But our mission today for you, our ever-curious listener, is to read between the lines of those charts. We are going to uncover the hidden, often misunderstood economics and physics behind industrial compressed air.
Right, because this is a utility that most of us rarely think about. Yet it is the invisible muscle powering, well, almost everything manufactured in the modern world.
Okay, let's unpack this. We are pivoting from a stack of dry industrial specs into a story about thermodynamics, brilliant acoustic engineering, and how fighting microscopic frictions saves literal millions of dollars.
What's fascinating here is the lineage of this specific machinery. The source text actually points out that Solaire has been at the leading edge of compressed air solutions since 1965.
Wow, so that's a long time.
Yeah, you are looking at decades of iterating on one fundamental mechanical challenge, and now, under the umbrella of Hitachi Global Air Power, they are producing what the brochure literally describes as bulletproof machinery.
Bulletproof. That's a strong word.
It is. It's built around this legendary Solaire air end, which is designed to be so durable that you can find these exact compressors operating in extreme environments worldwide, running as consistently today as they did, decades ago.
I mean, bulletproof is a very heavy claim for a corporate brochure, but as we get into the actual engineering they are putting into these steel boxes, you really start to see the physics backing it up.
You do.
And I want to promise you, listening right now, whether you are a seasoned facility manager actively trying to stop your factory from bleeding money, or you're just someone who loves a good aha moment about how the physical world operates, this deep dive is going to fundamentally change how you look at industrial hardware.
Absolutely.
We are going way beyond the bolts. But before we look at what this machine does to a company's utility bill, we really have to talk about what it does to the physical workspace.
That is definitely the right place to start, because the physical dimensions and, well, the acoustic footprint of this compressor represent a major paradigm shift in factory design. It's just a masterclass in spatial efficiency.
The footprint is tiny for its class. The brochure lists the dimensions at 53.2 inches long by 31.5 inches wide.
Right.
So just to visualize that, it's roughly the size of a standard executive office desk.
Very compact. But do not let that footprint deceive you. These machines are incredibly dense.
How heavy are we talking?
Depending on the specific model, they weigh anywhere from 1,044 to 1,156 pounds.
Oh, wow.
Yeah. You have a massive heavy metal heart packed into a remarkably tight frame.
Over a half-ton of spinning metal. But here's the specification that actually stopped me in my tracks. The noise level.
Yes.
The brochure states that it operates as low as 66 dBA. If you look at standard decibel charts, 66 decibels is roughly the volume of a normal human conversation, or like maybe a modern, quiet dishwasher running in your kitchen.
Exactly.
So please explain the physics here. Are you telling me a half-ton piece of industrial machinery crushing air at high pressure can sit next to you on a factory floor and you wouldn't even have to yell over it?
That's exactly what I'm telling you. It is a serious acoustic engineering achievement, and it all comes down to how they manage vibration.
Okay.
But to explain that, we first need to define what is actually making the noise. The brochure keeps referencing the air end.
I'm really glad you brought that up, actually, because I read air end throughout the entire text. Is that just a fancy industry term for the electric motor?
Not quite. The electric motor just provides the rotational power. The air end is where the actual physics of compression happen.
Oh, I see.
Yeah. Inside that heavy metal housing, there are two massive, precisely machined helical screws, rotary screws. As the motor spins them, these screws interlock, trapping ambient air and violently forcing it into an ever-shrinking space.
And I imagine that makes a racket.
Oh, it does. That mechanical process of crushing air generates an immense amount of vibration and mechanical noise.
Right. So if you bolt that violently vibrating air end directly to a rigid steel chassis, the whole machine essentially becomes a giant drum, right? Just amplifying the sound.
Exactly. The metal enclosure would act just like a speaker cabinet. So to get down to 66 decibels, Solaire engineered what is essentially an acoustic brake.
How does that work?
The integrated air end and the motor are mounted together, but they sit on heavy-duty rubber isolators.
Oh, I get it. It's like taking two tin cans connected by a string, where the string carries the sound vibrations and you just cut the string.
Yeah.
The rubber absorbs the kinetic energy before it can even transfer to the outer metal frame.
That's a really perfect way to visualize it. They sever the acoustic bridge, but they don't stop at vibration isolation.
What else do they do?
Well, a compressor still needs to breathe. It needs to pull in massive amounts of ambient air and exhaust hot air. Those intake and exhaust ports are usually screaming with airflow noise.
Like a jet engine.
Right. So the engineers added heavily insulated intake and exhaust louvers to muffle the rushing air, and they paired that with a specially designed low-noise fan. They're basically attacking the acoustics from all three angles: mechanical vibration, intake, and exhaust.
It's really impressive.
Yeah.
But let me challenge this from a business perspective for a second.
Sure.
Spending all this R&D money to make a compressor as quiet as a dishwasher feels, well, it feels a bit like a party trick. In a factory where you already have forklifts driving around and stamping presses slamming down, why does 66 decibels even matter?
Because the noise level dictates the geography of the entire factory. Historically, air compressors were so deafening that you had to banish them to a dedicated concrete compressor room at the far back of the building.
Oh, right. Which means you then have to run hundreds of feet of heavy steel piping all the way from that concrete bunker to the assembly line where the air is actually being used.
Precisely. And in pneumatic engineering, every single foot of pipe, every elbow joint, and every valve creates a pressure drop.
So you lose energy.
A lot of it. By the time the air travels 300 feet, you've lost a significant amount of the pressure you just paid good money to generate. But because the S energy is down to 66 decibels, you just don't need the concrete bunker anymore. You can install this heavy machinery right on the factory floor, directly next to the workers at the actual point of use.
So you completely eliminate the long pipe runs.
Exactly. You save installation costs and you preserve your air pressure. It fundamentally changes factory floor layouts, bringing heavy utility equipment into a much more human-centric design.
That makes total sense. You shrink it, you silence it, and you put it right where the worker needs it. But there is a danger there, isn't there?
What do you mean?
Well, if a machine is so quiet that it just hums politely in the background, you might completely forget it's even running, which means you might also forget what it is costing you to run.
Ah, yes.
And that naturally transitions us to the most eye-opening section of this material, the financial life cycle of compressed air.
This is a vital concept for anyone managing infrastructure, or really just a business budget. There is this deeply ingrained misconception that air is free.
Right, because it's just air.
Exactly. But mechanically compressing it into a usable utility is incredibly energy intensive. The source material cites data from the Compressed Air Challenge, highlighting that a staggering 82% of the total operating expenses over a compressor's life cycle goes strictly to energy costs.
82%.
82%.
So the actual physical machine, the heavy steel, the maintenance, the replacement part, all of that is just a tiny fraction of the cost compared to the electricity required to keep those rotary screws spinning.
It really puts it into perspective.
The brochure explicitly warns that in just 10 years, the electrical power cost to operate a standard compressor can be more than 6 times greater than the initial purchase price of the machine itself.
Think about that. 6 times the capital investment, just in operational energy.
Yeah.
It is a massive financial liability if your system isn't running efficiently.
Yeah.
And this is exactly where the brochure draws a very sharp, highly technical contrast between traditional constant speed drives and variable speed drives, or VSD.
Here's where it gets really interesting, because I am reading these numbers and I'm thinking, wait, if electricity is going to cost me 6 times the price of the hardware over a decade, why would any facility ever install a constant speed drive?
It's a fair question.
Isn't that just bleeding cash? If I can use a car analogy, a constant speed drive sounds like driving a vehicle with the gas pedal pinned to the floor 100% of the time, and you regulate your speed entirely by riding the brakes.
If we connect this to the bigger picture, Your car analogy is incredibly accurate for how a fixed-speed compressor operates.
Really?
Yeah. If your manufacturing plant needs exactly 100% of the air the compressor produces all day, every single day, without a single fluctuation, then a constant speed drive makes sense. It just runs flat out.
But almost no real-world factory operates like that, right?
Exactly. Demand fluctuates constantly. A worker puts down a pneumatic drill to go on a lunch break, or a secondary assembly line shuts down for a quick maintenance check.
And when demand drops, a constant speed compressor doesn't just slow down.
No, it doesn't. It reaches its maximum pressure limit and then enters a phase called unloading, or sometimes blowdown.
Unloading.
Right. It closes its inlet valve so it stops compressing new air. But the massive motor keeps spinning at full RPM just to overcome internal mechanical friction while venting pressurized air.
So it is literally burning electricity to do absolutely nothing.
Precisely. The variable speed drive solves this entirely. If you look at the part load performance assessment chart in the brochure, the physics of the VSD are completely different.
Walk us through that chart, because that seems to be the real visual proof of the savings.
Okay, so the chart tracks the relationship between the percentage of capacity, meaning how much air the factory actually needs at any given second, and the percentage of power consumed.
Okay.
With Solaire's single-stage lubricated variable speed compressor, that line is almost perfectly linear. If your factory suddenly only needs 60% of its air capacity, the VSD digitally slows the loader down, and you are only using about 60% of your power. It smoothly and instantly maps the power consumed directly to the capacity required.
So the VSD is essentially a highly intelligent gas pedal. It only gives the motor the exact electrical RPMs necessary to maintain pressure, down to the second.
Yes, exactly.
But the brochure points out another massive advantage to the VSD that goes way beyond just the electric bill. It talks about maintaining stable system pressure.
Yes, and this is a really critical engineering point. When a constant speed compressor is constantly loading and unloading, the air pressure in your factory's pipes is constantly fluctuating up and down like a sine wave.
Because it's starting and stopping.
Right. But a VSD, because it modulates its speed precisely, keeps the pressure inside the pipes perfectly flat and stable.
And why does a flat pressure line matter to the person actually managing the assembly line?
Because stable pressure improves the consistency of the manufacturing processes downstream. Think about it. If you were using automated robotic arms or precision pneumatic paint sprayers, fluctuating pressure means your robots move at slightly different speed.
Or your paint applies unevenly.
Exactly. Consistent air pressure means your tools operate flawlessly, which directly reduces the number of defective products coming off the line.
That is huge.
So the VSD isn't just lowering your utility bill, it is actively improving your final product's quality control.
That is a phenomenal connection. The quality of the invisible air directly impacts the physical quality of the product.
Exactly.
Now, there is another electrical term in the brochure under the VSD section that I need you to translate for us. It mentions a soft start feature, stating that it allows for unlimited starts and stops, avoiding high electrical current at startup, and eliminating the need for Y delta starters.
Okay, yeah.
What exactly is a Y delta, and why is avoiding it a good thing?
So this gets into the gritty reality of heavy industrial electricity. When a massive motor kicks on from a dead stop, it requires a massive surge of power just to overcome inertia.
Makes sense.
Historically, engineers used a Y delta starter to manage this. A Y delta is essentially an electromechanical switch. It starts the motor in a Y or star wiring configuration, which uses lower voltage to get the motor turning.
Okay.
And then a few seconds later, it aggressively snaps over to a delta configuration to hit full voltage and full speed.
That sounds violently mechanical.
It is. That aggressive switchover causes a massive jolting spike of electricity, a huge inrush current. And it puts tremendous mechanical stress on the motor's bearings and belts.
Ouch.
But worse than that, utility companies monitor these power spikes. They often hit factories with massive peak demand financial penalties if their machines draw too much juice at once.
Wait, really? So a factory could be hit with a massive utility fine just because their air compressor turned on too aggressively?
Exactly. It happens all the time.
Yeah.
But the VSD's soft start feature digitally ramps the motor up slowly and smoothly. There's no violent snap. Right. There is no massive power spike. Because there is no electrical penalty or mechanical wear and tear for starting and stopping, you don't have to leave the machine idling. You can have unlimited starts and stops, entirely dodging those utility fines.
It really operates as a highly engineered financial instrument just as much as a mechanical one.
It really does.
But this brings up a very practical question. We have established that energy efficiency is the absolute key to not losing massive amounts of money over a 10-year cycle.
Right.
But over 10 years, industrial environments are brutal. Things wear down, filters clog, oil degrades. How do you ensure the machine actually stays efficient in year 8 or year 9?
That's the real challenge.
According to the brochure, the answer is an entirely frictionless approach to maintenance design.
This is where the manufacturer's confidence in their own engineering is really put on paper. They offer what they call a 10-year diamond warranty.
10 years is a long time for moving parts.
It is. It covers that crucial air end for a full decade, and it provides 5 years of coverage on the motor, the VSD, the coolers, and the receiver tank.
Hmm.
But warranties of this magnitude always come with strict operational conditions.
Right. If they are going to ensure a half-ton machine spinning at thousands of RPMs for 10 years, they are obviously going to demand you play by their rules.
It is an engineering necessity. To maintain the diamond warranty, the facility is required to use genuine Solaire parts, participate in an ongoing oil sampling program, and strictly use their proprietary compressor fluid, which they call Solube.
Let's talk about Celeb because the brochure dedicates significant real estate to this fluid. It's clearly not just, off-the-shelf motor oil.
Not at all.
It's described as a biodegradable synthetic fluid with a high flash point of 505 degrees Fahrenheit or 263 degrees Celsius. And its primary claim to fame is that it prevents something called varnish.
Yes.
What exactly is varnish in this context, and why is it the enemy?
To understand varnish, you have to remember the thermodynamics we talked about earlier. Violently compressing air generates massive amounts of heat.
Right.
When standard lower quality oils are subjected to that extreme heat and pressure over time, the hydrocarbon molecules begin to break down and literally bake onto the internal metal surfaces.
Yeah, yes.
That baked-on sticky residue is varnish.
Okay, so if we use a medical analogy, it's basically like arterial plaque building up inside a mechanical artery.
That is exactly what it is. And remember, the rotary screws inside the air end operate on incredibly tight microscopic tolerances.
So if there's buildup.
Right. If varnish coats those rotors, it creates drag. It creates microscopic friction. Friction means the motor has to work harder to spin the screws.
Which means it draws more electricity.
Exactly. Which completely ruins the energy efficiency we just spent so much time establishing.
Oh, I see.
Solube is chemically formulated to resist that thermal breakdown. It cleans as it lubricates, entirely preventing the plaque buildup so the machine spins as freely in year 9 as it did on day 1.
So it's advanced chemical engineering required to protect the mechanical engineering.
That's a great way to put it.
And they are just as obsessive about physical filtration. The text outlines an optimal air filter that provides 10 times better filtration than standard filters, catching particles down to 0.4 microns.
That is microscopic dust.
Yeah. They also detail a fiberglass fluid filter that is coreless, non-metallic, and 20% more efficient than common cellulose media. Why so much focus on the filters?
Because a clogged filter forces the machine to pull harder to get the air and oil it needs. It creates a pressure drop.
Making the motor work harder again.
Right. Trying to pull air through a dirty filter is like trying to drink a really thick milkshake through a tiny clogged straw. The motor has to use more electricity to overcome that resistance. By using highly efficient fiberglass media, they minimize the pressure drop, keeping energy costs down.
But what really caught my eye wasn't just the filtration materials. It was the physical ergonomics of how a human being actually performs the maintenance. Because let's be honest, if maintenance is difficult, workers will skip it.
Yes, the human element of industrial design, it's so important.
The brochure explicitly notes that all standard maintenance access is on one single side of the machine. A mechanic doesn't have to walk in circles or unbolt panels shoved up against a wall.
Which is a huge time saver.
But the detail I loved most is the fluid filter itself. They deliberately inverted it. If you're listening to this and you've ever tried to change the oil filter on your personal car, you know the frustration.
Oh, absolutely.
You unscrew it from the bottom of the engine block, and gravity immediately pulls the dirty oil down your arm and all over the driveway.
It's the worst.
By simply designing the S-Energy compressor with an inverted, top-facing filter, gravity works for the mechanic instead of against them. The fluid safely drains back down into the system before the filter is completely unscrewed.
It minimizes lubricant loss, prevents a hazardous slip hazard on the factory floor, and saves the mechanic from an environmental mess.
It's just smart.
And that environmental consideration is baked into the entire chassis. The S-Energy units feature a fully sealed environmental protection pan integrated into the bottom of the frame, designed to capture any accidental spills.
Nice.
Furthermore, the internal cooler, which needs regular cleaning, is mounted on sliding rails. A mechanic simply removes a few bolts, and the entire heavy cooler slides out like a kitchen drawer for easy access.
It feels like they looked at every possible excuse a tired maintenance worker might have for skipping a service interval, and they just engineered the excuse right out of the machine.
That is the exact psychology of the design. They're creating an ecosystem built for compliance. By making the maintenance physically frictionless with single-side access, drawer-style coolers, and inverted filters, they systematically reduce human laziness and error.
Right.
But physical design is really only half the battle. They pair that with aggressive digital oversight.
Yes, the brochure spends time on the digital brain. There is a 7-inch color Solaire touchscreen controller, the STS, which handles trend graphing of operational parameters and power monitoring.
It's a very slick interface.
It also has sequencing capability, meaning it can coordinate up to 16 different compressors to act as a single network. And then there is the AirLink's remote monitoring system.
AirLinks pushes the machine's telemetry to the cloud. It allows facility managers to remotely monitor key parameters like pressure, temperature, and hours of operation.
From anywhere.
From anywhere. And more importantly, it pushes warnings and fault alarms directly to a smartphone or computer. The machine isn't just sitting in the corner waiting for a mechanic to notice a red light flashing.
Right.
It is actively communicating its mechanical health to the people responsible for it. This combination of frictionless physical maintenance and proactive digital monitoring is really the only way a company can realistically guarantee the conditions of a 10-year warranty.
So, what does this all mean? We started today's deep dive by opening what looked like a dry technical catalog, but we've discovered that an air compressor isn't just a heavy steel box that blows air.
Not at all.
It is a highly engineered financial instrument where acoustic physics, thermodynamics, chemistry, and digital software all intersect. From isolating vibration so it can sit safely next to a worker, to using variable speed drives to smoothly map energy consumption to factory demand.
Yeah.
And utilizing 505-degree synthetic fluids to fight microscopic friction. Every single mechanical decision is relentlessly optimized to lower that massive 82% life cycle energy cost.
This raises an important question, though. We have spent this entire deep dive hyper-focused on the compressor itself.
Right.
It is the heart of the operation, and it is a spectacular piece of engineering. But the final pages of the source material introduce a much broader, more critical concept: total compressed air systems.
The system, not just the box.
Exactly. The text emphasizes that true efficiency requires analyzing the entire circulatory system of the factory. You can't just drop a good compressor into a bad network.
What else is in the network?
The Hitachi Global Air Power System includes wet storage, which are massive holding tanks that stabilize the air before moisture is removed. It includes refrigerated or chemical desiccant dryers that pull water vapor out of the air so it doesn't rust the factory's tools.
Oh, that makes sense.
It includes complex inline filtration, dry storage tanks, and flow controllers. Every single component must be mathematically matched for capacity and pressure.
So, if I understand this correctly, you could buy this perfectly engineered, infinitely variable, whisper-quiet S-Energy compressor, install it, and still completely fail at saving money.
Precisely. If you have the world's most sophisticated VSD compressor, but your wet storage tanks are undersized, causing the machine to short cycle, or your desiccant dryers are unmatched to your airflow.
Or your distribution pipes are riddled with tiny, hissing leaks.
Right. Are you actually saving energy? The compressor is just the central hub. And I think this challenges us to look at any complex system we manage, even in our own lives, businesses, or workflows. Are we spending all our capital and energy trying to polish the central hub to absolute perfection, while remaining completely blind to the slow, invisible leaks bleeding efficiency out of the broader network?
That is a brilliant and honestly slightly intimidating way to frame it. You can't just engineer a perfect heart. You have to treat the whole circulatory system.
Exactly.
I think that is the perfect thought to leave you with today. Thank you for joining us on this deep dive. Keep questioning the hidden mechanics and the invisible utilities of the world around you, because as we saw today, even something as ordinary as a blast of compressed air is hiding a literal masterpiece of modern engineering. Until next time.